Hello everyone, I'm Shruti and this is the part of my term paper. Permanent magnetization in ferromagnets. So what are ferromagnets? Well, ferromagnets are the materials which we commonly see as permanent magnets. So ferromagnetism is the basic mechanism by which certain materials form permanent magnets or are attracted to magnets. In a ferromagnet, we see ferromagnetic ordering in which all the spins are aligned together, giving rise to non-zero magnetization and giving a particular direction to the magnetic field that they produce. Now let's have a look at how this is happening. So consider two atoms nearby. In the diagram, the arrow represents the spin of the electron. Now there are two possible configurations. Either one shown here with in which the spins are anti-aligned, or the other one in which they are parallelly aligned. Now the first state is known as singlet state with energy, let's say EF, and the second configuration is known as triplet state with energy, let's say ET. Now let me define a quantity J as ES minus ET. The use of this J would appear later, but for now, consider this. If J is positive, that would mean that the energy of singlet state is more than the energy of triplet state, implying that triplet state is a more favorable configuration. That would further imply that the electrons in the neighboring atom would try to parallelly align. Now, what does this mean is if I have an electron, let's say with spin up, it would try to align its neighboring atom parallelly. They would try to align their neighbors further and ultimately giving us ferromagnetic ordering. Now let's have a look at it a bit more analytically. If I write down the Hamiltonian of the ferromagnet, it would look something like this. Now the second term is due to the external magnetic field, and this is the term responsible for paramagnet, while this first term is the interaction term which we have just encountered. Now notice J here. This J is same as the J I defined earlier. The subscript I and J represents the ith and the jth atom in the lattice. Now, I know that I can, my spin is related to magnetic moment and my magnetic moment is related to magnetic field. So I can relate or in better words, manipulate this first term in terms of a magnetic field, let's say BMF, which would give me a Hamiltonian entirely in this form, which is a form of paramagnetic Hamiltonian with the effective magnetic field as B plus lambda m. Lambda is the parameterization and m is the magnetization in my uh, material. Now notice that I have taken same magnetic field for all the sites. That means I have taken the main field theory approach where we assume that the potential is approximately same for all of the points. The model that I am the model I am using to understand ferromagnetism is known as Weiss model. Now, if I know the solution of a paramagnet, that would mean I can obtain the solution of ferromagnet just by modifying the magnetic field to the effective magnetic field. The solution of the paramagnet looks something like this, where M is my magnetization, Ms is my saturated magnetization. Obviously, a material cannot have infinitely large magnetization. There has to be some upper limit because there are limited number of electrons and limited number of spins. And there is a quantity written here as Bj. Now, Bj is my Brillouin function, which has the parameter j and depends on y. where I have defined my Y in terms of magnetic field and temperature. Now, if I try to write the solution for ferromagnet, I need to modify this B to something like this. Alright, now I have two solutions between magnetization and Y. First this one, where magnetization is a Broglie function of Y, and the other one is this, where magnetization is a straight line. Magnetization and Y are following a straight line, where the slope between M and Y is directly proportional to the temperature. Now, if I try to plot these, let's try to plot this for first zero magnetic field. What you can see here is this curve is the Broglie function, and these lines are the different solutions of the second equation for different temperatures. If I have a very high temperature, I'll have very large slope, let's say this one. And the point of intersection between this line and the slope, that is the solution for these two equations, would be only one point, m equal to 0. Now, if I start to decrease it such that after some certain temperature, let's say critical temperature, in which the slope the slope of Broglie function and the slope of this line at origin is same, but I'll find that the temperature is below further critical temperature. The point of intersection is not only having m equal to 0 solution, but also some non-zero solutions. That means if these solutions are favorable ones, stable ones, then my material would be having non-zero magnetization in the absence of magnetic field. Well, this is exactly what we observe in permanent magnets or ferromagnets. So far our theory is going well and good. And for the sake of completeness, when I have some magnetic field, my straight line solutions will shift towards right or left depending on the sign of magnetic field, and the number of point of intersections is always one independent of temperature. Also, the sign of magnetization would be same as the sign of magnetic field, exactly what we observe. And if one tries to do the detailed analysis, one would find the critical temperature to be something like this. Now, how do we know if the non-zero magnetization points in the absence of external field that we are finding are stable and more favorable? Well, thermodynamics. So the principle of energy minimization tells us that the free energy is always minimized with respect to the unconstrained parameters whenever to achieve the stable equilibrium. Now let's have a look at free energy and magnetization curve. So at T greater than critical temperature, what we see here is just one equilibrium point that was as expected, m equal to 0, where it is stable. Good. When I decrease the temperature at T equal to critical temperature, the curve is flat bottomed around origin. Upon going further below critical temperature, what I find is a double well curve or a Mexican hat curve, where there are two non-zero magnetization which are having minima, meaning stable configuration, and the m equal to 0 configuration is an unstable configuration, which is, I think, not surprising, which is what we wanted to see because that is what we observe. So, what is happening? One more thing to notice that is happening here is at critical temperature, the particle can lie anywhere in this region. And when I decrease the temperature even a little bit, it will this potential curve will form a double well. No matter how small, there will be a curve. There will be double well. So it will fall into either of this direction and giving me non-zero magnetization. But which direction it would prefer is completely spontaneous. The symmetry which once it was having in its Hamiltonian, that it was rotationally symmetric, is now broken, and there is one particular direction in which the magnetization is pointing. This is known as a spontaneous symmetry breaking. Now, one more thing before closing it, that this point and this point, these points are having same energy. That would what that mean is the particle can oscillate from this configuration to this configuration, and certainly material do. The magnetization in them do oscillate, but the time period of such oscillation is very large. It is larger than even the age of universe, and that's why we do not observe them. So what's the conclusion? The conclusion is that that we saw that there, in the absence of magnetic field, there is possibility of non-zero magnetization, which is happening below critical temperature. And by the way, this critical temperature is also known as Curie temperature in ferromagnetization case. And this non-zero magnetization is pretty stable as per what thermodynamics tell us. So what we see as a result is the permanent magnet in a daily life, or in technical terms, ferromagnets. Thank you.